All right, we should be rolling here now. I hope everyone had a good weekend. um, I sent out an announcement. I hope you all got that I had fixed that video. Did y'all get that? Okay. That last example that I got hung up in class on, I went ahead and worked it out, resolved it. So that's that. Here's our schedule. I've changed it, everyone. So I don't want there to be any surprises. We were supposed to have our next exam after the drop date, but we're going to have today's class 8-2, next class 8-3, next Monday 8-4, next Wednesday 8-5. 8-5. The exam, it'll cover 7-3 through 7-6. We'll do, it'll also cover 8-1 through 8-4. And then that's next Wednesday, and then next Friday is the drop date. So what I'll do is I'll grade those Wednesday night, Thursday, and if you're in a situation where you think you're going to want to know your grade or something, you'll have to call me, text me, email me, right? And I'll let you know what your grade is, and that way you can drop if you want to drop. I'm not going to drop anyone. Like, you have to drop yourself if you don't want to be in the class, okay? All right? Okay, we'll talk more about that later. We are going to start today's class by not doing series right away. I was hoping I could knock something else out before. The section on the, what was that thing that I told you to read? Center of mass? Okay, so for centroid, again, these are all the formulas. They're all in the book. The whole idea of you reading the book, reading this section, was just to see how we can apply these formulas to some real problems. So a lot of times in engineering physics classes, they give you the formulas, and it's just a matter of can you apply it. So I'm going to get straight to a problem. What we have is this number 40. We're given a function y equals square root of x, another curve here, y equals 0 and x equals 4. What happens is if you draw those three curves, you get an enclosed region right there. And what we're trying to do is find the centroid of that, the center of mass. So I put together a real quick little demo to explain what's happening here. This is the square root of x. This is that region, like a real physical example of that region, right? So this is an object. I'm going to assume that this object is homogeneous, which means that the density of the object is the same throughout. Although it's not, because cardboard and the way they make these things, there can be some slight variations in its density. Does that make sense? Okay, but if this is a homogeneous lamina, is what we call it, a lamina, then there is some point at which this thing would balance, if I tried to balance it, right? And so I already found it right here. You can kind of see that little hole there, but I'm not gonna stick my pin in that thing. I'm just gonna see if that's the center of mass. I'm just gonna put it pretty close to it there. Whoa. Whoa. Okay. So was that convincing enough? Right there. That's it. Right there. That's the center of mass. So if I put that on there, it's going to balance, right? Yes?
Yes.
Okay. So if I just move it just a little bit, it's going to fall. So finding that point, that center of mass, is important. A lot of you do physics problems, right? When you do physics problems, you look at every object pretty much as a point mass. So instead of looking at it as some weird lamina, you just say this lamina is equivalent to all the mass concentrated at one point, right? And so where is that point? Where is that center of mass? It's right here. So to compute it, we have to use the two formulas for x bar and y bar. X bar and y bar give us the x coordinate and y coordinate of the centroid, of the center of mass. And the formulas are 1 over a, integral blah, 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 1 over a, integral blah, blah, blah. A is the area of the lamina. So you have to first find the area of this. And to find the area, that's an integral, isn't it? It would be integral from a to b of just what's underneath this curve, right? So square root of x. So I worked through all this here. Here it is. So here's first of all my area. Area is the integral from 0 to 4. That's because I'm going from 0 to 4 of the square root of x, which is the curve. And then I, convert square root of x to the 1/2. Find the antiderivative. Plug in 4, plug in 0. I get 16 over 3. All right? Once I do that, I'm ready to compute x bar. X bar is 1 over the area. 1 over 16/3 is the same as 3/16. Integral from 0 to 4 of x times the function. So instead of having just root x, it's x root x. And then I multiply these two together, I get x to the 3/2, and then I go through the antiderivative again. Is this clear on what I'm doing or not? You sure? Ron? Yes. Yes, I'll put this out there. Yeah. Yeah, don't worry about copying all this down necessarily. And what I get here, once I do that, is 2.4. So that's my x bar. Then to do y bar, that gives me the y coordinate. What I need to do is 1 over a again, integral from 0 to 4, but this time it's half of the function squared. And my function is square root of x, so again, I go through all this and I get an answer, and it's 0.75. That's what I'm going to ask you to do on a test. All right? I'm just going to give you a region, and then you have to compute the centroid. Not going to get any more complicated than that. When you take further classes, maybe in Cal 3, your instructor might go over this, where you look at a lamina that has it's non-homogeneous, meaning that the density of the lamina changes throughout. So maybe this is more dense towards the end and less dense towards this end, the left end. Okay, then the center of mass would change. So all that happens is that your formula changes. Okay, but again, it's just an integral. All right. So the way I did this to figure out this center of mass is I used my computer at home to print out that function. I printed it on a piece of paper, and then I put it on a piece of cardboard and traced it out and cut out the cardboard, and there it is. Okay. Here's another one. The next example, oh, I don't have it here. I'll just put it on the board real quick. It was the region between, you have sine x, here's sine x, and here's cosine x, something like that, whatever. It's like this. So here's cosine x, here's sine x, and you're taking this region in here, right there, and trying to find the center of mass. And that's it right there. That's that region blown up. And you can find the center of mass. It's about right here. Again, I'll try it here. Whoa, pretty close. Yeah, that marker is making this even more difficult. Like I said, it's not homogeneous, so it's kind of tough to, well, you believe it or not. I mean, it's about right there, okay? That's a little better, okay? So there's my center of mass. Make sense? No? Yes?
For the exam, do we have to memorize the formulas or you can give it to us?
The formulas you will not have to memorize. Good question.
You're going to give us, like,
Find the centroid. I'll just, yeah, you'll have the formula somehow. I might just write them on the board that day. Here's another way, just FYI, a very non-precise way of getting a center of mass. If you have an object like this and you want to find its center of mass, what you can do is you can tether it or just hang it from like a string from a point like this. Whoa. And then drop it. And then let me make sure it's hanging where, damn it, get over here. Just hang it from any point. I'm trying to let it hang, but okay. Let's just say it's hanging. You draw a line straight down, okay? And then you hang it from another point and draw a line straight down. And then to be real precise, get a third point and draw it straight down from there. So we're letting gravity act as, and then where they all cross each other is your center of mass. Here's something kind of cool. I don't know how this is going to work. I haven't tried it. If I take this and I throw it across the room, right, it's going to, I don't know what the hell it's going to do. It's probably going to hurt one of these guys. But try and look at just the point. I don't know how this is going to work. Oh, okay. You see how the point, anything you throw on Earth travels parabolic, right? It's a parabolic path, okay? Yeah, I'm going to throw it again. So now what I want you to do is focus on just the point. The point's not going to go up and down because this is spinning. Look at the point. Oh, I took out my tablet. What did the point look like it was doing? Could y'all tell what the point looked like?
You can focus on it. You can see it's
The point is just parabolic, right? So it's that center of mass was moving through like a parabola. Everything else happening around didn't matter. Yeah? It's kind of cool, huh? What, this thing?
Yeah, he's spinning it and it's moving the projectile motion. That's what we're learning.
Oh, okay, that's cool.
So we know how much energy you just threw that with.
Nice. You mean math and physics, they actually work together somehow? I don't believe it. All right, so that's it. The problems out of the book, I forgot which ones they are. So I'll get that assignment to you. I'll email it, or maybe we'll do it at the end of class here. We are ready, though, to get into today's topic, the Big Daddy, the beginning of series. Again, this will all be posted on the web, so don't sit here and try and copy everything down. What's more important is that you don't just sit there and go, what the hell, what the hell, what the hell, I'll figure it out later. Ask questions, okay, if you have questions. All right, we ended last time with the idea of sequences, right? Sequences are just a list of numbers, right? A sequence of numbers, and we were looking at the different properties of those things. And now what we want to do is talk about a series. Not sequence, series. A series, or an infinite series, is the infinite sum of the terms of a sequence. So a sequence is a list of numbers, right? A series is add them all up. So if I've got a sequence, a sub n, that was some number, comma, some other number, comma, that was my list of numbers, right? Then the series that corresponds to that sequence is a sub 1 plus a sub 2 plus a sub 3 plus dot, 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 and dot, dot, dot means forever, right, for us? So that just means keep adding them all up forever. So we introduce a new notation here, which is the sigma notation, right? Summation, have we seen that already? We've seen this. This means we want to add things up, right? Now, what are we trying to add? A sub k. A sub k are the pieces, are the different terms of our sequence, right? Remember how this index works? Start at k equals 1, then the next one will be k is 2, then k is 3, and k is 4, and the sum means add them. So if I start at k is 1, we've got a sub 1, plus, now 2, plus, and where do I stop? Infinity. So I never stop, right? Do you see how that notation works? All right. So now, that's the series. That's the infinite series for a sequence. Next major idea, the idea of partial sums. So if we're given a, what is this? A what? A sequence, right? If we're given a sequence, then we have this idea of not adding them up forever, but adding partial sums. So the first partial sum, that's what we call it, is adding just the first term of the sequence, a sub 1. Nothing else. So it's just a sub 1, right? The second partial sum is a sub 1 and a sub 2 added together. The third partial sum is a1, a2, and a3, right? I could keep doing this. S sub 4 would be the first 4 terms. S sub 5. So S sub n is the sum of the first what? N terms. So we call it the nth partial sum. So here's what it looks like as far as a formula. So what's the difference between this and what we just saw? Yeah, the infinity, where we stop, is replaced by n, isn't it? So this just adds up the first n terms. Notice, though, that when you add these up, right, all of these should be numbers, shouldn't they? Like whatever a sub 1 is, that's a sub 1. Add a1 and a2 together, that's an answer. There's an answer to that, right? You get a number. Add the first 3 together, you get another number. You keep doing this, you keep on getting numbers, don't you? So all these numbers down the left side create a new sequence of numbers, don't they? You see what I'm saying? So S1 is just the first term of this sequence. S sub 2 is the first 2 terms of that sequence added. S sub 3 is the first 3, and so on and so forth. Oh, man. All right, so the partial sums gives us a new sequence. Start with the sequence. It's a list of numbers. The infinite series is adding them up forever. The partial sums is adding them up, either one of them or 2 or 3 or 4. That creates a new sequence of numbers. Any questions? You could if you wanted to. You mean create a series? Or yes, by adding you could. We're not going to, but you could. Yeah. So here's your first example. Can you all see that? Can everyone see that? Is that too low? It's all right? I just don't want to reveal everything that's coming. Secret. All right, so here's our first one. Let a sub n, and what I try to do in these notes is separate the sequence from the series by using red and blue, okay? Let's see. I think 75 might. Let's see how this works. All right, that should be good. So we have the sequence. A sub n equals 1 over 2 to the n. So the first term of this sequence is 1/2. That's what we get when we plug in 1, right? Then we get 1/4, 1/8, 1/16, right? This is a sequence. Now we want to get the series for that sequence. What is this right here? That's summation. So that's a series. Is it the series forever? Is it everything added forever or no? No. What do we call this then? The nth partial sum. This is the nth partial sum. So I started to list out these values. S sub 1 is just the first guy, right? Which is 1/2. S sub 2 is the 1/2 plus the next guy, which is 1/4. Add these two together, you get 3/4, right? S sub 3, add those two together, or those 3 together, 1/2 plus the 1/4 plus the 1/8, you get 7/8. You'd have to get like common denominator there and everything, right? S sub 4 would be the first 4 added together. And then I could keep going, couldn't I? What do you think the question is going to be here? What's what? What's the limit? See, what about this sequence here? We know that this sequence, where are these things going? Where are they headed? They're getting closer to 0, right? So the terms of my sequence are getting smaller, right? But the terms of the series are doing what? They look like they're increasing. They're getting bigger and bigger and bigger, right? And they look like they're getting closer to 1. So what I've done is I've listed out, this is the series listed out in sequence form, right? It's the new sequence that's created. And what I've done is I've drawn or I've had the computer draw for me, both of these together. So a sub n was the original thing. We said, look, that starts out 1/2, right? 1/2 is here. 1/2, then 1/4, then 1/8, then 1/16, 1/32, and then they keep on getting smaller and smaller and smaller, right? So we knew that our original sequence went to 0. But what about the series? The series, when you start adding them, it was 1/2, then 3/4, then 7/8, right? And that sequence looks like it's converging to 1, doesn't it? Looks like it is. Yay or nay? So that's what I just said. We can see that the original sequence is convergent, went to 0, and it looks like the series is convergent also, isn't it? Looks like it. So does this mean that if the original sequence converges, then the series must also converge? What do you think? And you want to say yes, but it's probably no. Is that what you said?
If you're doing a sub n,
Because I want to say yes.
what's that 90%?
So if this guy, if your sequence converges to a number, and then you start adding them up, is that answer guaranteed to converge? That's what we start to ask ourselves. So let me give you another example and see if we can look at this one. Different sequence, right? The previous one was 1/2 raised to the n. This one's 1/n. So list out the first few terms of this sequence. 1, 1/2, 1/3, 1/4, keep going forever and ever. Start adding them up now. My first partial sum is 1. Second partial sum is 1 plus 1/2, what's 3/2. Third partial sum, 11/6. Fourth partial sum, 25/12. What's happening here? There's the sequence. Now let me show you the picture. So I put here a sub n, you could tell that that was going to 0, right? Right, that would start out as 1, then went 1/2, 1/3, 1/4, 1/5. That's going to 0. When we start adding them, that sequence is going like this. Does that look like it's flattening out? That's why I put a question mark here. Does it look like it's flattening out? Well, I could get into the Mathematica right now and show this to you, but I'm not going to because of time. The further out I go, it just keeps growing. So it's not flattening out like the previous example. The previous example, this is converging to 1. So as the further you go out, it gets closer and closer to 1, but it never goes past 1. Where with this one, even though it kind of grows slower and slower, it's still going up.
Because you're just adding smaller and smaller amounts every time.
Well, yes, but didn't we have this discussion? Even though you're smaller amounts,
Yeah, but that is a different way of doing it.
this is exactly that same thing. See, what in both cases, right? When you have in both of these problems, I'm going to do a new page just so we can see this. When you took the 1/2 to the n versus the 1/n, when I start adding these, when I do this one, the first one is 1/2, then 1/4, then 1/8, and I keep going, right? Every time I go out, I'm adding a little more, right? And it's a positive amount, so I'm adding something, and I'm doing it forever. Here, I start out at 1, then 1/2, then 1/3, then 1/4. So every time I go out, I'm adding something and it's positive, right? But there's completely different things happening with those sums. One of them is getting closer to 1 without actually ever getting there. The other one just keeps on getting bigger and bigger and bigger. So sometimes it blows up, like this one blows up, goes to infinity. Sometimes it converges. And the question for us is, when does it do that? But both of them are we're adding something. Keep on adding, all right? All right, so back to this now. Let's look at the conclusion of this. So in this problem, we can see that still our original sequence was still going to 0, right? but our summation, our series diverged. It's going to get infinite. So just because this converges, we need not have the series converge. So when does it? That's the big question of the day. When will your series converge? And that's what we're going to have to kind of hang tight for, okay? Another example. Look at this one. A sub n equals 2n over n plus 1. Somebody quickly tell me what this sequence converges to. This sequence. I'll give you a hint. L'Hopital. If you let n go to infinity here on top and bottom, you get infinity over infinity. Use L'Hopital rule once, you get 2, don't you? 2 over 1. So this sequence converges to 2. So you start out at 1, then it's 2, then it's what? 1 point something, right? And then something, and then keep on doing this. If you do it, it's going to come out to be 2. Hold on a second. Plug in 1, we get 2 over 2. Plug in 2, we get 4 over 3. That should be 4/3, right? Yeah, that kind of confused me a little too. 4/3, there we go. Well, it can jump, it can go above 2 and come back, but yeah, that should be right. Yeah, but that's going to mess these up now. Well, it's okay because my picture won't be messed up. The computer did it. Let's see if we can. So 7/3 here. 7/3 plus 6/4. 28 and 18 is 30, 46 over 12, something like that. Reduce it on your own. Who cares, right? We could add those up. Yay or nay? Okay, so look at what, before I get to the series, what's different about this sequence from the 2 previous problems? Where did the sequences in the previous 2 problems go? 0. Didn't they? They went to 0. This sequence goes to what? Any guess as to what's going to happen with this series then? It's going to what? Converge? What do you? Diverge? Why? I mean, give me some reasoning. Start out with 1, right? Add to it 4/3. Next time, add 6/4.
That's the pattern of the second problem, because you're adding numbers that are still at 2, so you're essentially adding something that's close to 2 every single time.
Yeah, each of these is getting closer to 2, right?
Yeah.
So I'm like taking a number, I'm adding something that's close to 2. And then next time adding 2 again.
So you're essentially almost putting 2 every single time.
Yeah, I'm basically stacking 2 on top of 2 on top of 2 on top of 2 forever, right? What should happen? That should get infinitely large. See, before, what was happening is we kept on stacking, right? But each time was less. So it was like getting smaller each time. Sometimes that meant it converged, sometimes it diverged. It all depends on how much you're stacking each time. If it's smaller and smaller each time and gets smaller fast enough, then it'll converge. But I was hoping you would see that because this goes to 2,
It's like increasing by fast.
it's super fast, right? I mean, 2 each time. So look at the picture. Look at how quick this happens. The sequence wants to get close to 2, right? So every time I stack 2 on top of 2, look at how quickly the series diverges. It's just, it's off, right? It's taken off. Just about. They're spread out, yep. Okay? Are there any questions? Are y'all kind of getting this idea? We still have to get in here and do some of this mechanically, but I'm trying to get you to see what's happening like visually. So check this out. And this is going to turn out to be a theorem later. If our sequence goes to L, if our sequence has a limit, and that limit is not 0, like in this problem, this sequence was headed where? To 2. If our sequence is headed to anywhere other than 0, what can you tell me about the series? It has to diverge. Look, let's say our sequence goes to 10, right? Our sequence is headed to 10. But if I keep on stacking 10 on top of 10 on top of 10, that series is going to blow up, right? So maybe you're like, okay, what if this is converging to 1/1000th? Well, 1/1000th is still 1/1000th. If I stack that up 1,000 times, I'm going to get 1, right? 2,000 times, I'm going to get 2. You see what I'm saying? So like, as long as this limit is a number bigger than 0 or less than 0, then if I keep stacking them, my series is going to diverge. The only way that I can ever get my series to converge is if the sequence is going to 0. Well, if it converges, the sequence has to go to 0. That's what we can say. Hang tight though. Here's what we have so far. And these are in the book as theorems, but I just want to give it you in a more kind of laid back fashion. If our sequence, all right, this is a sequence, isn't it? A sub n. If our sequence, when we let it go to infinity, if that sequence doesn't exist, if that limit doesn't exist, give me an example of a sequence that doesn't exist. The limit doesn't exist. Someone gave this to me at the end of class last time. I think it was you. A sequence that does not exist. The limit doesn't exist. Sine. Sine, maybe it was you. I don't remember. It came from somewhere around in this area somewhere. Yeah. Sine, right? Sine n. What does that sequence do? It oscillates up and down, but it's like dot, 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 dot. But it doesn't go anywhere, right? That limit doesn't exist, right? So if that happens, okay, if your limit doesn't exist of your sequence, or if the limit does not go to 0, then I can guarantee you the series is divergent, right? Here's what I can also say. If the series does converge, so if that series does go, when we start adding things up, if it's headed towards a number, it's going to stay fixed at that number, like the first one we looked at that went to 1. If that happens, if a series converges, I guarantee you this must happen. The sequence has to go to 0. Okay? The sequence has to go to 0. And I put a thing here to be very careful on this. This if-then statement. Do y'all know how if-then statements work? It's a logical thing. If this is true, then this is true. It doesn't work the other way around, right, necessarily? So the other way around is not true. Just because a sequence goes to 0 does not mean the sequence, just because a sequence doesn't, start over. Just because a sequence goes to 0 does not mean the series converges. And didn't I show you that already? It was this one, right? This one was an example where the sequence went to 0, but the series diverged. That's one of the biggest mistakes that I see from students, is that they'll say, oh, they'll look at the sequence, they'll say it goes to 0, series converges, done. It's not the way it works. Any questions? All right, this is just some terminology. Given a sequence, then S sub n is a new sequence, which is the sum of all those pieces, right? If that series, which is this sequence, if that series converges, goes towards a number, then we say that the series converges. C is the sum of the series. C is what it adds up to, well, it doesn't add up to B, that's what it approaches. If the series diverges, then we say that the series is divergent. That's just language. And now we are going to get into the 3 very important common series that we will face in a Cal 2 class and later on in this chapter. The 3 series that we're going to study now are the geometric series, the harmonic series, and the telescopic or collapsing series. These are the three most important ones. You ready? Here we go. Start with geometric. Okay, go ahead and take a minute to write that one down. All geometric series look like that. That looks wonderful. Okay? That enough time? The form that you're going to see it a lot in is this one right here. But this is just to help us see what's happening. A in the problem is a constant. All right? So what we have is a constant in front of something, r, being raised to these powers. So if you start at k equals 1, what's r to the 1 minus 1?
0.
It's r to the 0, which is 1, right? So a times 1 is a. Then we let k be 2. 2 minus 1 is 1. So now we get r to the 1. So a times r. Then ar squared, ar cubed. So any geometric series looks like a number plus a number times a number plus a number times that number squared plus a number times that number cubed, and that pattern continues forever. Okay? That's called a geometric series. The question is, does this series converge or not? Well, let's see. What am I doing? Well,
What if R was a fraction?
yeah, what if r is a fraction, right? Like, what if r is 1/2? And let's just say, for the sake of right now, let's just pick a to be 1. What would this be? 1 plus 1/2 plus 1/4 plus 1/8, right? What's that? Start at what?
Would it start at 0?
Would what start at? This right here?
If A is 1, it starts at 1.
But then wouldn't it just be 1 minus 1?
It just deems on what you consider your.
Yeah, 1 minus 1, but r to the 0 is 1.
That way you only have A.
That's why you just have a.
It just depends on what your R value is.
That's right. It is going to depend on r. So this example, it was 1/2 plus 1/4 plus 1/8 plus 1/16. Didn't we already look at that a minute ago?
Would diverge. It would convert.
What did that one do? It looked like it went up to 1, right?
Yeah.
You see what I'm saying or no?
Yes.
Well, this is 1/2, 1/4, 1/8, right? Add 1 to it, and that should be 1 plus 1 should go to 2, shouldn't it?
Yeah.
Forget that that's there. Isn't that 1/2 plus 1/4 plus 1/8? And I showed you from a picture that 1/2 plus 1/4 plus 1/8, that all went to where? Got closer to 1 when you add them up, right? Then if you throw a 1 in front of that, that means it's getting closer to 2. Follow that or not? But what if r is 2? Because you said 1/2, right? What if r is 2?
They diverge.
Then it's 1 plus 2 plus 4 plus 8 plus 16. That thing's going to explode.
Your R value.
Your r is going to dictate it, right? Okay, so as mathematicians, we'd like to know when it does converge. The instinct would be when r is bigger than 1, right? It would do what? When r is bigger than 1, it would diverge, and when r is less than 1, it would converge. That would be the idea. That seems to make sense, but mathematically we have to show it. So let me show it to you, and then see if you can follow it. This is a very, very, very cool proof of this. So first of all, Let me take out the space here that I put in there. Bring this up. Okay, so this is the sum right here, right? That's a geometric series. So what I do first, this is to show that this, we're going to answer this question. First of all, S sub n is the what? How do we say it? It's the nth partial sum. So let's just look at what it would mean to add up the first n guys, right? So the first n guys would be a plus ar squared plus all the way till I get out to what? Ar n minus 1. That's important because if I stop at n, then when I plug n in up here, n minus 1 would leave me n minus 1, wouldn't it? Is that okay with you or not?
Yes.
Now, out of nowhere, I want you to take that equation, multiply both sides by r. What would you get? Multiply this side by r, that side by r. Left side by r, you get r s sub n, right? This side becomes what though? ar squared, ar cubed, and then the last one becomes, instead of ar to the n minus 1, it becomes ar to the n, doesn't it? Aren't I just adding an r to each one of these? So increasing the exponent on the r's by 1 each time? Do y'all see this? Especially people who are like going on and doing like real like math, pure math. This is what you do all day long, this sort of thing. Okay? No questions? Okay, now out of nowhere, I want you to take this one and subtract this one. Okay, so write this one down. S sub n, that's right here. Subtract from it r s sub n, which is this one right here. What happens? Lots of shit's going to cancel, right? This AR is going to get wiped out by that AR. This AR squared is going to get wiped out by that AR squared. Everything's getting wiped out, right? The only thing left is the A in the very beginning, and then what else? The very last term on the other one. Because this A times r to the n minus 1 actually got wiped out by the one right in front here, which was ar to the n minus 1 was right in front of that one, right? Right there. So that one and that one go away. So the only thing left is the front and the back. How in the hell would you have ever thought to do this, right? This is what mathematicians do, is they brutalize themselves by just taking swings and trying and doing all sorts of weird things until it freaking works, okay? So someone probably spent the majority of their life trying to figure this out. Okay, so now this and this becomes this, right? Still there? Now factor out the s sub n here. Factor it out. And lastly, divide both sides by 1 minus r. What we have is a formula for the nth partial sum. It's a minus a r to the n over 1 minus r. Now what I'd like to know is what happens is I let this n go to infinity, right? Because I'm trying to figure out where that series is headed. So take the limit as n goes to infinity of this and tell me what happens to this. If n goes to infinity, what happens to this? Well, the only thing that n is acting on is the r right here, isn't it? So tell me a little bit about r to the infinity. Well, don't we already know that if r is less than, the absolute value of r is less than 1, that means it's a fraction? If I take a fraction, start raising it to powers, it gets smaller, right? And so this thing, that thing should go where? Where would this thing go? Where would that go, right there, if that was a fraction? That whole little piece right there would go to 0, wouldn't it? Okay? But if r is bigger than 1, then I start raising a number bigger than 1 to powers. That's going to get huge, isn't it? So that thing's going to explode and go to infinity. Which gives us two conclusions. a geometric series, right? The geometric series, if the absolute value of r is less than 1, so it's a fraction, right? Smaller than 1, it converges to a over 1 minus r. Where's the a over 1 minus r coming from?
From the original sequence.
This piece right here, right? When r was a fraction, r sub n went to 0. This whole thing went away. What was the only thing left up here then? If that's all gone, if that's 0 up here, the only thing left is what? A over 1 minus r, right? So we get a over 1 minus r. But if the absolute value of r is bigger than 1, that thing explodes and goes to infinity, so it diverges.
So R always has to be positive.
Nope. You can have as long as the absolute value of it is less than 1. So this is the big daddy. You should probably write this one down. So I'm hoping that what you see is that this should be pretty easy to tell if it converges or diverges, right? All you have to be able to do is tell me what r is, right? If you can figure out what r is, and you can determine that r is a fraction smaller than 1, you can tell me it converges, and you can tell me exactly what it converges to. If the r is bigger than 1, you're done. The series diverges. Here's some examples that I put together. Yeah, I will. Still see it? So here's an example of a geometric series. So here's the series right here. A r to the k minus 1. I picked a to be 1 and r to be 3/4. 3/4 is less than 1, isn't it? So this should converge. Where should it converge to?
1 over 1 minus 3/4.
This should converge to, this blue one up here should converge to, you said it right. This should converge to 1 over 1 minus 3/4, which is 1 over 1/4, which is 4. And you can see, well, it's really hard to see, but that's a 4 right there. See the 4? 1, 2, 3, 4. And you can see that that series converges to 4. Where on the other example over here, I picked a to be 1 and then r to be 3/2. 3/2 is bigger than 1. So you can see not only does the sequence diverge, the series diverges also. We okay with this? There's a lot of tired people here today. So your next test grade is happening now. You know what I'm saying? Think about it that way. Oh man. What the hell? Go ahead and write that one down. The top one there. The 4 to the k. All right, here we go. Find the sum of this. Can y'all read that all right? Sum k equals 1 to infinity of 4 to the k over 7 to the k minus 2. Now, we already know this is geometric because that's what we're talking about, right? But again, like on a test, how are you going to know it's geometric? Just by looking, you're going to have to somehow see it is. Let me help you. This is equal to sum k equals 1 to infinity, 4 to the k over 7 to the k times 7 to the negative 2. Do you agree with that? I'm going to put the geometric series formula over here. Sum k equals 1 to infinity a r to the k minus 1, right? That's what a geometric series has to look like. It has to look like a plus ar squared plus forever. We know it converges if the absolute value of r is less than 1. It diverges if the absolute value of r is bigger than 1. And if it converges to a over 1 minus r. That's what a geometric series does, right? So I need to make that look like that. So the first thing you should be thinking to yourself is, does my index start at 1? Okay, doesn't always, in all problems that they present to you, doesn't always start at 1, okay? So you have to pay attention. Does it start at 1? Yes. Does it go to infinity? Yes. Do I have a number in front of a number raised to a k minus 1? Well, I don't even have k minus 1s, do I? Do I? Not yet. I'm about to make them. I need to create k minus 1s. So anytime I need a k minus 1, what I'll do is this. 4 to the k minus 1 plus 1 over 7 to the k minus 1 plus 1, then 7 to the negative 2. So all I've done is really nothing. I haven't changed the problem, have I? I came in here with this plus 1 minus 1 here and this plus 1 minus 1 here. We've done something like this before, haven't we? Added and subtracted something to make things work. I'm doing it again. Now my next line here is summation k equals 1 to infinity of 4 to the k minus 1 times 4 to the 1 over 7 to the k minus 1 times 7 to the 1 times 7 to the negative 2. So what am I doing here? Separating it out. Yes, question. Yeah, I'm going to bring it up in just a second. First thing I want to do is get all my k minus 1s first. So y'all see what I've done? I've taken this, I've split these right here, right? I've said 4 to the k minus 1 plus 1 is the same as 4 to the k minus 1 times 4 to the 1, because if you have the same base, you add the exponents, don't you? Same base, add the exponents. So here's where I am now. Out of room. Equals summation k equals 1 to infinity of, well, how do we want to do this? 4 to the k minus 1 times 4 over 7 to the k minus 1 times 7 to the negative 1. What did I do there?
Just combine the 7.
Put the two 7s together. 7 to the 1 times 7 to the negative 2. You add the exponents, you get negative 1. That's why I waited to bring it up. Now I'm going to bring that 7 up. That 7 is going to come up and hit the 4 and become a what? 28, right? 7 times 4 is 28. So now I've got this. Summation k equals 1 to infinity of 28 times, check this out, 4 over 7 to the k minus 1. What did I do there? These two things are raised to the same power, aren't they? The 4 is raised to the k minus 1 and the 7 is raised to the k minus 1. Anytime two things are in a fraction, they're both raised to the same power, you can switch it over to a fraction, the whole thing raised to a power, can't you? All we're doing is just massaging this thing into a geometric form, just so it can look like our formula. But there's a lot of little rules and properties of exponents and stuff we have to know. You sure there's no questions?
So then from there, you know your A and your R, you can just use the little rules or not?
Yeah, now we know A and R. So I'm actually going to try and make more space again. All right. I understand some of your situation. If you're still too tired, I still look at it as people sleeping on class. I don't appreciate it. So, all right, try and snap out of it. Okay, so I have finally gotten to a point where I've got summation k equals 1 to infinity. Here's my a, right? A is 28. R is 4/7 to the k minus 1. That's exactly like the geometric series, isn't it? So I now identify a to be 28. I identify r to be 4/7. And definitely that's less than 1, right? If it were a negative 4/7, I'd be looking at the absolute value, but it's not, so that's why I didn't put absolute value. So this series converges. And it converges to a over 1 minus r, which is 28 over 1 minus 4/7, which is 28 over 3/7, which is, you have to multiply 7 on top, 7, 140, what is that, 196 over 3? I think it's 196 over 3. Does that go in there? 196 over 3. I believe that's right. That's what that series converges to. And we would leave it as a fraction, just like that. We don't need the decimal. You actually want to leave it because it converges. That means it's getting closer and closer to that. It's never actually going to get there, but the series is getting closer and closer. A good example of a geometric series, everyone, is the example where you take 1/2 plus 1/4 plus 1/8. And the example that I learned, I can remember this vividly. It was like a 5th grade science class where a teacher stood at one side of the room and she said, okay, I'm going to walk halfway. Right? Did I already do this in here? Yeah, right? Whatever. And then I go half again. So that's a 1/4. So I've walked half plus a 1/4, right? Then halfway again would mean 1/8. So now I've done a half and a 1/4 and an 1/8. Then I go halfway again. That's half, 1/4, 1/8, 1/16. Halfway again. Now if I keep doing that forever, I'll never hit the wall. Theoretically, I can keep going half, right? But I'm getting closer and closer to being how far? 1, right? The distance from one end to the other was 1. This was half, right? So the whole distance would be 1 unit, whatever it is, 1 mile, 1 foot, whatever. Half, 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 forever. Converges to 1, but you never get there. That's why you don't want to round, because if you round, you probably are going to get there and go past it. See what I'm saying? Okay. Next one. Now you might be sitting here, and I think I heard this last class, is like, what's the point of all this, okay? What's the point of all this? I'll give you a real quick reason as to why this is important. And I've already touched on this before in class. Let's just take e to the x. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus forever and ever and ever. So you take this function that's very confusing to most people. Most people are like, what the hell is e to the x really? I mean, really, what is it? It turns out that e to the x can be represented as a series of polynomials. You see, these are all power functions. X cubed, x squared over a number, x cubed over a number, x to the 4th over a number. So if I take a bunch of these forever, that's what e to the x is. So what we have is that most functions, they have to have certain characteristics, but most functions can be converted into what is called their power series, right? It's a series of powers of x. It's called its power series. And then what happens is if you want to integrate this or differentiate this, all you have to do is differentiate or integrate this, and this you can do, like if I want to take derivative of this, I just do derivative of each one, right? If I want to integrate, I just integrate each one. Integrating this is easy to integrate that, right? These are just powers. Antiderivative, that's 1/2 x squared. Antiderivative, that's x. Antiderivative of this, well, you'd have to account for the 2 factorial, but it'd be like 1/6 x cubed, right? This is what this is what a computer sees. A computer works on this, and it cuts it off somewhere because the computer can't go forever. So the computer will cut off at a certain tolerance. Whatever's built into the language of the computer, whatever the code is written to say, I'll go out 50 terms, right? And that's where I'll cut it off. So everything your computer does is an approximation. But there are some functions, like e to the negative x squared, that you cannot integrate. There's nothing you can do by hand to get that. But if you expand it out into its power series, you can. So we're starting off first with series of numbers. And we're seeing if we can look at some characteristics of convergence and divergence of just numbers. Just give me a list of numbers. And then we're going to say, let's now look at a series of powers of x and talk about when that converges and when that diverges. All right, so we're kind of building up to it. And this is the big difference between the two founders of calculus, Isaac Newton and Leibniz. Isaac Newton created power series. Leibniz had no idea what power series was. So when they got together, everyone always gives Newton more credit because Newton's power series kind of blew Leibniz away. Like, you know, you hand Leibniz an integral and he'd be like, can't do it, sorry. And Newton would be like, yeah, I got it. I'm just going to convert to a power series. I'm good. So much more powerful. All right. That's where we're headed. What about this guy?
Change of base.
When you're looking at something like this, you want to be thinking probably, look, I see like, oh wait, hold on, change those n's to k's.
That's why.
Yeah, sorry about that. I need k's in here.
There we go. Hey, got it.
Your book uses n's, okay? Your book always uses n equals 1, n here, n here. I don't like that because I reserve the n for the nth partial sum. And so I always use k as my index. And the only time I ever use n is when I'm going to stop at n. All right, so I see like numbers to powers, right? K, and maybe I can get this geometric, right? So let's try and massage it. I think what I'll do is I'll just do a little scratch work here. Let's see what we can do with 5 to the 3k times 7 to the 4 minus 2k. You don't need logs. I need to change this into an a r to the k minus 1, right? That's what I'm looking for. Okay, can I do this then? Is this the same as 5 to the 3k times 7 to the 4th over 7 to the 2k? So all I did here was I brought this was like a 7 to the 4th times 7 to the negative 2k. And then I dropped that down. So we okay with that? Now I need those to be k minus 1s, don't I? Plus 1, yeah, but right now it's a 3k and a 2k. Isn't 5 to the 3rd to the k the same as 5 to the 3k? Because something to a power, you multiply the powers, don't you? Times 7 to the 4th over, how can I do the bottom one? 7 to the 2nd to the k?
Would you spend them out?
Yeah, let's go ahead and figure out what's 5 cubed. 125. So I've got 125 to the k times 7 to the 4th. I don't really want to multiply that out. Over what? 49 to the k? which equals, now I have it to k's, don't I? But what do I need? K minus 1, right? So now you can do the k plus, or k, I can do k minus 1 plus 1. So I'm going to go 125 k minus 1 plus 1, 7 to the 4th times 7 to the 4th, over 49 k minus 1 plus 1, which is 125 to the k minus 1 times 125 times 7 to the 4th, all over 49 to the k minus 1 times 49. Everyone following that? Now these are both to the k minus 1, right? So I can put those together in parentheses in a fraction. So I've got 125 over 49 to the k minus 1 times 125 times 7 to the 4th, all over 49.
You cancel the, make it 7 to the.
You could cancel, but I actually think, I mean, I was done a while ago, but this is A, right?
Oh, yeah.
And this right here is R. And what's the deal with R? It's bigger than 1.
Whatever.
It diverges. I could have I mean, just from the experience, we could have stopped right here. Because we could say, look, I know that all that's going to happen now is I'm going to get a k minus 1 plus 1, right? So I'm going to get that 125 and that 49 to be in a fraction. And that's bigger than 1. So R, the absolute value of R is bigger than 1. This series diverges. It is geometric, but it diverges. How fun was that? Any questions? You got to play with these things.
What happens if R is 0?
Good question. If R is 0, the whole series is 0. Right? So it's just 0 plus 0 plus 0 plus 0.
A
Right.
times 0.
Well, you'll have A. That'll be it. And then also R, if R is 1, it diverges. Did I put that up here? Hold on.
I don't think you had like the little bar underneath there.
Where is it?
All equal to.
Yeah. If R is bigger than or if the absolute value of R is bigger than or equal to 1, it diverges. Because if it's 1, if R is 1, then you have A plus A plus A plus A plus A plus A plus A, and that's going to go big, right? If, well, you mean like in all this? Like here I did the summation. Well, as long as you somehow show me it's scratch work, like this was to show you this is scratch work. And then when I was doing my scratch work, what I was able to determine was that when I get down to it, I'm going to have this inside my sum, and the R is bigger than 1, so I'm done. So I was just trying to save us some rewriting sum. Either way, yep. All right, so that's the first type of series, geometric. The next one is harmonic. Harmonic. You like that? So what does harmonic look like? Harmonic looks like a constant C over K. So anytime you have a constant over a number that keeps getting bigger by 1 each time. So I've got C over 1, C over 2, C over 3, C over 4, C over 5, C over 6, blah, 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 forever and ever. That's called harmonic. And I actually did this one earlier, didn't I? I did 1 over n. And so our sequence was 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. And we saw that that one diverged, didn't it? So it says that all harmonic series, all of them, always diverge. And the question is why? And this is somewhat tough to explain. So I think what I'm going to do is I'm just going to I'm just going to not explain it. Well, only because of time, all right? It's really a time constriction. I have all the work written down. What happens is that as you look at the nth partial sums, you look at, like if you look at the first partial sum, you get C. When you look at the second partial sum, you get C times 1 plus a half. All right? When you look at the fourth one, you get C times 1 plus a half plus a half. Then when you go out and you have to jump from the fourth to the eighth one, you get C times 1 half, or sorry, C times 1 plus a half plus a half plus a half. So doesn't it look like when I go out, like on the fourth partial sum, I'm adding 2 halves to this. When I go out to the eighth one, I get 3 halves added. When I go out to the 16th partial sum, I get a 1 plus a half, 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 half. So what's happening is that the further I go out, it's like adding up half plus half plus half plus half. And if I keep adding halves forever, it's going to diverge. All right, so if you want to go through and actually look at that, you can, but you can also just take it on faith. That's all the work for it. There's an example. There are 2 examples. So here's an example. I've got 2 over k. This is harmonic, right? Harmonic because the denominator just keeps on going up by 1, right? 1, 1, 1, 1. And the c on top, the constant is 2, right? So I've got c over k. And you can see that the sequence converges, right? The sequence, it converges. But the series diverges. Look at this one over here, 1 over 4k. Does everyone see that the constant is 1/4? Like you can almost like factor, like pull that 1/4 out in front. It's still going to be harmonic and it still diverges. So our sequence goes to 0, but our series diverges. The challenge for harmonic series is to figure out its harmonic.
Do they always go to 0?
Yeah, what?
Sequence?
The sequence will always go to 0. That's right. But the series always diverges. With harmonic only though, right? Okay, so let's look at this one. Notice I didn't give this one in summation notation, right? I didn't give you the sum because a lot of times if someone gives you the summation notation, it's way too easy to see that it's harmonic, right? So, because all you're looking at for harmonic is basically looking at the denominator keeps going up by 1 each time and being able to pull a C out. So it's a little harder if someone gives you the series written out, you know, something plus something plus something plus something, and you being able to see it's harmonic. So does anyone see this one?
3 over 5n or 5 or
What is it? Sum k equals what? 1 to infinity of 3 over 5k? Is that right or not? Let's see. Plug in 1, we get 3/5. Plug in 2, we get 3/10. Plug in 3, we get 3/15, but 3/15 is 1/5. 3 over, let's see, 20, and then, where are we, 5?
3 over 25?
No, hold on.
Towards total.
3,
Or 3 over.
no, I think I messed up my last one here. This is supposed to be right. Let me see. 1, 2, 3, 4, 5. Let's see. What are we supposed to get for 5? 3 over 25. I don't know what the hell. Unless it's something else. Hold on. Was it something else? What else could it have been?
Well, nothing times 5 is going to get you a 7.
Yeah.
On the top gives you a 3.
So fix that. Y'all see that right there? Fix that. That all right? So this is harmonic. See, a lot of people will say, well, wait a minute. The denominator is not going up by 1 each time. The denominator is going up, what, by 5 each time? So it's not harmonic. But that's not the way you need to look at it. You need to look at this as being sum k equals 1 to infinity of 3/5 over k. Because the 3/5 is the same the whole time, right? So your C is 3/5. That's harmonic. So you would say here harmonic, so it diverges. On a test, I'm going to want you to be able to convert this. You can't just look at that and say, like, you can't just write diverges, right? You have to say harmonic and show me the formula for it. It's not going to be like a multiple choice test, like converge or diverge, converge or diverge. You still got to have the work behind it. True or false? Any questions on harmonic? Harmonic's pretty clean. Geometric we have to really work at to make it, to get the A and the R.
So in reality, the series is 3 over 5, 3 over 5 over 2, 3 over 5.
3 over 5 over 3.
Okay.
Yeah. Okay, let's look at this one. Telescopic. Now, for a telescopic series, it's hard to give you like a formula. We just have to get into a problem and you'll see how it works. Okay, so the first one, don't write this down, just follow me, and then we're gonna do one by hand, okay? So here's the series. K equals 1 to infinity of 1 over k times k plus 1. So let's take a look at this. We get 1/2, let me make sure I did this right. Plug in 2, we get 1 over 2 times 3. Plug in 3, we get 1 over 3 times 4. Yep. Okay, it's not geometric and not harmonic. Why?
The harmonic you tell because it has two k's as a denominator.
It's not harmonic because it doesn't
I mean,
diverge.
you have the constant on the top, but your k is it's a multiplicative of k. You know what I mean?
It's not going to diverge, right?
Kind of.
Like you
Like
have k times
1 over k by itself is harmonic, right?
yes, but the fact that
1 over k plus 1 by itself is harmonic, but they're being multiplied. So
There is no constant. Is it not harmonic because it doesn't diverge? I mean, it's going to go to 0, right? The denominator goes up so high.
well, this right here and here, that sequence converges to 0. But the question is, does the sum converge or diverge? Let me approach it this way. Why is it not harmonic? Because for harmonic, I would need a constant times, or a constant over something that keeps going up by 1. So let me try something. Looks like I go 2, then 3, then 4, then 5, right? So it looks like my denominator is going up by 1. But what's in front of, if I'm going to say this is my k, I start at 2, then I go 3, then I go 4, then I go 5, then what's the number in front of this one right here? What's in front of, what's on top? 1? 1? Well, I'm saying I start at 2, then I go to 3, then 4. This would have to be a 1, but the constant here would then be what? If 3 is, it would be 1/2. Then if the 4, the next constant would be 1/3. So my constant's changing as I move out too, and your constant can't change, right? So it's not harmonic because we don't have that. It's not geometric. Why? These aren't going up by powers. Geometric is all about powers, right? R to the n. Are these all going up by powers? This is 2, then what, 6, then 12, then 20. They're going up by, they're jumping by a factor, a multiple, but it's not going up by powers. Do y'all see what I'm saying? So it's neither one. Okay, so check this out. We start with this, and we turn it into this. Recognize that? PFD? What does PFD stand for? Partial fraction decomposition. We did that when we were doing integrals, partial fractions. So remember how to do this? You take it and you say, oh, it's a linear factor that gives me an a over k minus a b over k plus 1. Then you had to do that little thing and let k be this and get your numbers. I'm not going to show any of that work, but you could turn this into this, right? Now, that means that this series is equivalent to this series. Yeah? Just rewriting this as this. Now start plugging in some things. Let's plug in 1. We get 1 over 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. Do y'all see that? And it keeps going forever. Now let me look at the nth partial sum. The nth partial sum. I don't want to list them all. I just want to list the first n of them. So it's this. So I get 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus blah, 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 blah. Then I get down to the end here, don't I? I'm going to have to go a little smaller here. You see everything canceling? Negative 1/2, positive 1/2. Negative 1/3, positive 1/3. Negative 1/4, positive 1/4. Basically, the second term here, the second guy in the parentheses is wiping out the first one of the next parentheses, right? And that pattern continues. The second guy wipes out the first. The second wipes out the first. Second, first, second, first, second, first. When I get to this last one, or second to last one, the second one wipes out the first. But this second one and this one has nobody to wipe out, does he? So that's the only one that's left, isn't it? And then the one in the front.
Shouldn't it be minus on the previous two?
I forgot to put minus in there, yes. Thank you. Yeah. Thanks for catching that. Those are minuses because there are minuses in here. So minus, minus, they wipe out. All that's left is one and this one, right? This is where the whole idea of telescopic or collapsing comes from. Have you ever seen like the old-fashioned telescopes, like this? And then how they put them away? Like that, right? They do that. Or collapsing, it's like a bridge. You got two ends and everything in the middle collapses away. So that's what's happened here. Everything in the middle collapsed or telescoped down to just get the two ends, right? And you get this. So now if that's what the first n of these add up to be, I want to know what happens if I let n go to infinity. So let n go to infinity here. That's just 1. And n to infinity here, you have a fixed over infinity, 0. So that goes to 1. So that series adds up to be 1. And there's the picture of it. You can see the terms are going to 0. And the terms of the sequence are going to 0. And then you add them up, it goes to 1. Okay. We're almost done. All right, we're going to do this one. Find sum k equals 5 to infinity. So notice that we're starting at 5, right? Starting at 5. So let's see, is this geometric? Well, with geometric, isn't the k minus 1 is the power, right? The power is the thing that keeps changing. And here it's the base that changes, right? So this is automatically not geometric because it's not the exponent that keeps on changing. Is it harmonic?
Well, no, because you have something that's squared.
Yeah, you have squared. You don't have just k or a multiple of k.
Yeah, because you can take the k and k times k minus 1.
That's right. So I'm kind of, without geometric and without being harmonic, I have to figure out what it is. So the one thing you can do to try and get your hands around it is to write out the first few terms. This would be equal to, let's see, plug in 5, right? Plug in 5 first. 1 over 24 plus 1 over, now 6 squared, 36, so 35 plus 1 over 48 plus, yep. So that just keeps going, right? I could go all day here. Now, right now what we can say is this. this inside here, right? This sequence that we're adding up the pieces, that does go to 0, doesn't it? Each one of those are getting smaller. They are going to 0. We always want to look at that because what if those were going to 2? What if those were getting closer and closer to 2? This would diverge, right? But since they're going to 0, I know it could diverge or converge. You all understand what I'm saying? Since each of those terms right here, since each one is getting smaller and smaller, is going to 0, I don't know. The only thing I would know is if it goes to a constant other than 0. Then I could say it diverged. So I'm still stuck. So what I'm going to do now is I'm going to take a look at this 1 over k squared minus 1. I'm just going to do some work on this. I can factor that to be k plus 1 times k minus 1, right? And I know that that's equal to a over k plus 1 plus b over k minus 1, right? So I'm going to do partial fraction decomposition on this. So since we've done this so many times and we like it so much, I'm just going to skip right down to this now. So I'm trying to find a and b, right? So this is where I come in and I say let k equal negative 1. If I do that, I get 1 equals negative 2k. So k is negative 1/2. Then I can let k be equal to positive 1, and that gives me 1 equals 2. Oh, sorry, that shouldn't be 2k. That should be 2a. 2b, so b is positive 1/2. We've done this already, right? So I'm not really going to spend a lot of time on that. So the original problem becomes this. I'm trying to find the sum k equals 5 to infinity of a over k plus 1, right? Negative 1/2 over k plus 1 plus positive 1/2 over k minus 1. Y'all see what I've done? No questions? Sure. So let me write out some of these terms. And what I'm hoping for is the collapse. So start out at 5. What would you get? Negative 1/2 over 6. I'm not even going to simplify that. Plus 1/2 over 4. Plus, now, negative 1/2 over, k is 6 now, right? 7 plus 1/2 over 5. Uh-oh. Shit. Plus negative 1/2 over, where am I? 7, 8, plus 1/2 over 6. Right?
But they're all being added.
Nothing was canceling, right? Until I got to this one. 1/2 over 6 is going to cancel with the negative 1/2 over 6. But none of these were canceling, were they? Okay, this is a good example because you got to see this. Sometimes the telescope the way it collapses is really weird. Yeah, like to finally start to see the pattern of cancellation takes you listing out a bunch of stuff. So I'm going to keep going here. I'm going to try and go as far as I can on my paper here, widthwise. Plus negative 1/2 over what, 9? plus 1/2 over 5. Y'all still with me or not? Okay, let's do one more. Negative 1/2 over 10 plus 1/2 over, where am I, 4? 6. Wait a minute, hold on, did I get this right? I don't know why it's 5. I have no idea why it's 5.
It should be 7.
Thank you. 7 then 8. I'll be honest, I know why it was because I didn't even look. I don't know why I put 5 there. Just had a feeling that was going to be the next number. Okay, this keeps going, right? Now, the only way to properly tell what's happening with the collapsing series is to look at what's happening with the pattern in the beginning, but also to look at the pattern at the back. So what I'm going to do is I'm going to put below this plus dot, 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 right? Now, I'm going to write out, I'm going to start at the very end. What would the last term? Oh, you know what? I need to be summing, change this, hold on. Change this in front, just change that S sub n. Okay? Because that's what I do. I want to take the nth partial sum. So S sub n is this. So what would the last one be? If you plug in n for k, negative 1/2 over n plus 1 plus 1/2 over n minus 1, right? That would be that last one? Y'all still follow that? Okay, what's the one right in front of this? So what are we plugging in? I'm going to put it up above here. Here's n minus 1. This is what we get when we plug in n. Negative 1/2 over n. Is everyone all right where that n comes from? Yes? No? I'm plugging in n minus 1, right? N minus 1 into that formula. N minus 1 plus 1 is n. So that's now an n. When I plug n minus 1 into this formula right here, I go n minus 1, which gives me n minus 2. So plus 1/2 over n minus 2. Now the one before that, I'm actually plugging in n minus 2, aren't I? Negative 1/2 over what? N minus 1 plus 1/2 over n minus 3. Anything cancel yet? Yeah, that first one right here and this last one here. Let's go one more. I'm going to plug in n minus 3. Damn, it's already 234. So I get negative 1/2 n minus 2 plus 1/2 over n minus 4. All right, you ready for the canceling? See if I can do this in fun. I'm going to start at the beginning. I'm going to start at the front of the telescope up here. Does anything cancel with the negative 1/2? 6 right here, this one. That one right here, right? So those two kill each other off? Yes? I'm going to connect them. Okay? What about the one with the 1/2 over 4? No. How about negative 1/2 over 7? Yes. Right there. How about the 1/2 over 5? Okay. Negative 1/2 over 8? Yes. Okay. How about negative 1/2 over 9? Yes, it will over here somewhere, right? It will? And the one right here next to it already got killed off. So the only thing in the front of the telescope that was preserved was the 1/2 over 4, 1/2 over 5, and that's it, right? This killed off with something over here. I don't know where it is, but it's over there somewhere, right? It would be the next, and then inside the next one. So it looks like the first, sitting inside the parentheses, the first guy is killing off the second guy, but two terms away, right? The first guy kills off the second guy 2 terms away. So let's go down to the bottom here. This first guy should kill off the second guy 2 terms away. That one right there. So this guy and this guy cancel. How about this guy? He's a second term, right? Second terms are killed off by first terms 2 in front of them, right? So this guy should get killed off by something in front of him. From somewhere over here. First guy should kill off second guys 2 terms away. There they are. The second guy should be killed off by the two in front, the first guy 2 in front, right? So is this guy going to go away? Yes, by something in front. First guys kill off second guys 2 terms away. There is no 2 terms away. This guy is preserved. First guys kill off second guys 2 terms away. There is no 2 terms away. So the only thing left in this are the things highlighted in yellow. Right? So S sub n, put it up here, S sub n equals, what's 1/2 divided by 4? 1/8? And then 1/10? So I'm going to put 1/8 plus 1/10 plus this right here, negative 1/2 over n plus negative 1/2 over n plus 1. Now, what do? That's your nth partial sum, right?
Take the limit.
Take the limit. Good. Take the limit as n goes to infinity of S sub n. And the last 2 terms vanish because we have a constant over infinity, right? Constant over infinity. So all that's left is 1/8 plus 1/10, which is 18 over 80, right? Common denominator. Which is, what goes into that? 9 over 40. I think that's reduced. 9/40ths. What do you think? Questions? Okay, I'm going to put the notes out on the web for you today. I'm actually going back to my office right now. I have to do a faculty evaluation at 3:30, so I'm going to go back to my office. I'm going to put this out on the web, and I'm going to send out an announcement with your homework assignment. It'll include problems from the centroid and problems from the series section. We're pretty much done with the 8.2 though. Yes. Before our test, yes. So Wednesday, 8.3, which is going to be convergence tests, and 8.4, which is more convergence tests, if I'm not mistaken, yeah. Make sure you do your homework, okay? This test is going to come fast, and there's a lot of material here. So,
Are you gonna tell us like last time, like one problem here, like this section?
I don't know. I don't know if that's a good thing or not. I'm not sure.
Stick to your word.
What I am going to do is not make it where you can take home the problems and redo it, because I don't like having to regrade everything, which I did, by the way. So if you're interested in your grade, I do have your updated grades.